Hello, today a very geometric and beautiful exercise. I have the stereographical projection from the North Pole onto the plane. I want to find a way to be able to compute the length of curves on the sphere by computing some similar quantity on the images of those curves on the plane, or the shadows of those curves on the plane. And this is in effect changing the geometry of R2 in a way that R2 becomes indistinguishable from S2 in all aspects, including curvature, area, and of course length of curves. Let's see how we go about this. For that, let's recall how we computed the length of curves in the first place. So I did several videos on this notion of length of curves, so please check them out as well. I touch upon very delicate issues there, but anyway, we have learned that if we have a C1 curve, then its length is integral of its speed. You take derivative and you take norm and you compute. Now, this cannot, of course, give me the what I want, and I need to modify this formula. And to get some idea, let me go back up there and show you why this has to be changed. So suppose you have a curve here, and you have just an exact copy of it, except that it's a bit further away from the origin. On the sphere, one of them is going to be shorter and closer to the North Pole than the other. So although these two curves are parameterized on the same interval, they have exact same velocity vectors. Their length is going to be very different on the sphere. So that means the way I compute the length of this gamma prime of t has to take into account also the location where that is located. So the same curve here compared to that will have a different length. And this new length that I'm going to talk about, I'm going to denote it by putting this little index g here. So it's going to be the g length of gamma prime of t. And gamma prime, there's nothing special about it. I'm going to compute not just for gamma primes, but any vector. So any vector you give me in the plane, I'm gonna replace its Euclidean norm with a new norm, which I designate by g. And the job is, of course, to find out exactly what this g has to be. So let's begin. And after I have that, I want to have this formula correct. That means if I compute the length of a curve in a very similar fashion, except that I take g norm of the speed, the velocity vectors, I end up having the length of the image of the curve on the sphere. So let's look at a simple case. We have this curve here, gamma, which parameterizes our circle of radius capital R with a constant speed. So that means the Euclidean norm of the derivative of the curve is always the same value, and we can assume it's r, and the curve is parameterized on 0 to 2 pi. It travels it just once. Now its image on the sphere, this psi o gamma, will be again a circle of a different radius. So this time this little r. And according to my would-be formula, I must recover this parameter, the length of the curve on the sphere, from integrating the g norm of the derivative. Because of all the symmetries, I assume, it's expected that this to be independent of t, because that only rotates my picture above, and I don't think there is any reason to declare the length of this to be different from the length of that, even the g length of those, because their images up here are just same length in R3. And if this is going to be a constant quantity, then it has to be just equal to little r. So what I ended up having is that if I have a vector of length r in the Euclidean sense, capital R, then it in the G norm, it must have a length of equal to little r. So the vectors that are tangent to the circles, in other words, they are perpendicular to the radial direction in R2, scale by this factor little r over capital R. So capital R is a quantity given in terms of this V. It is just the distance to the origin of the base of my vector. But what is this little r? It's kind of not closely associated with little v, but it must be, of course, calculable, and I do it exactly right now. So I want to find the ratio little r over capital R, and if I take a cross section, all I see is I have this unit circle. I have a projection from the North Pole onto the x-axis, and I want to see what this little r has to be. And after some trial and error, and that was a kind of very satisfying exercise, I call this angle here up here theta. As a result, this becomes 2 theta, because both are looking at the same arc. One of them is central angle, one of them has its tip on the perimeter, and we know from early geometry that one is the interior angle is twice. Anyway, this little r is then exactly equal to sine of 2 theta, right? So you just drop a perpendicular, and that is, we know, equal to 2 times theta, sine of theta, cosine of theta. And I rewrite this in a strange way as tangent of theta, as a formula in tangent of theta. The reason being is that I know tangent of theta. The edge across from it has length r, and adjacent to it is just radius of the circle, which is 1. So tangent of theta is just capital R, and therefore little r is computed in terms of capital R by this. So what I ended up computing is that if I have a vector perpendicular to the radial direction, something like this V, then its G norm is little r over capital R, but then I computed that that is exactly 1 plus r to power 2 of the Euclidean norm of V. And this capital R is again the base of the vector, distance of the base of the vector to the origin. Now that is just certain vectors that are perpendicular to the radial direction, but general vectors will not be in that form. So for that, I also need to find a new class of vectors whose G norms I can compute. This time, I take a curve that starts at the origin and radially escapes from it to the infinity. And because, again, of the symmetry, I can imagine that the cross-section is actually the xz coordinate system. Therefore, I have just gamma t equal t0. So this point, this is gamma t at that point. And what is the image up here of that point? So we have computed this little r, and that is, and this is 1. This is a perpendicular angle. So this is 1, that is r. Therefore, you can also compute this from Pythagorean. And therefore, if little r equals this much, then that will be the vertical height. And this is interestingly called, I later learned that this is famous and is called the double angle parametrization of a circle, because, well, you have this green half line and it maps exactly on half of the circle. So it really produces a parameterization of half of the circle. Now, the length of this vector here is going to be equal to the length of the corresponding derivative norm here. So I compute the derivative of psi gamma, and I take its R3 norm. This is all calculation, and it ends up being 2 over 1 plus t squared. So in other words, I computed that if you have a unit vector here, because, well, the derivative of that gamma prime t is just 1, 0. That if you have the unit vector escaping from the origin, then its G norm will be 2 over 1 plus t squared times its Euclidean norm. And this, incidentally, is exactly the same factor as above. So t here is the distance to the origin. And putting these together, what I have computed is that, yeah, so for such vectors v that are perpendicular to the radial direction, or those that are parallel to the radial direction, the norm, the G norm, is just 2 over 1 plus r squared of the Euclidean norm. Is this enough to give me the G norm of any other vector? So if this is just a B, can I calculate the G norm of that? No, that information is not enough. What we need is also to know the angle, the G angle between V and W. And that is 0 because the corresponding vectors up here in the sphere are actually going to be perpendicular. So V, remember, corresponded to a tangent of one of the horizontal circles, and this W is vertically up. So here they are perpendicular. That's an indication that I should declare V and W, which are perpendicular in the Euclidean sense, to also be perpendicular in this G dot product. So this G is not just a norm, it's a dot product, and the norm of a vector is just a V dot V and then square root. So now under these three conditions, I can actually compute this, because what I will do is rewrite B as a linear combination of V and W. And now I'm going to dot product with itself. Then I will use the linearity of the dot product, right? This breaks up, and V1, V dot V is just the length of V squared. V dot W is 0 according to this, and W dot W is just the square of that. So that way, now I have a way of calculating the norm in this altered geometry of any vector. And therefore, my formula, which was this, now makes sense, because whatever gamma prime is, whether it's perpendicular to the radial or parallel to it or any other vector, I know how to compute its G norm. And the way I compute it is, again, recall that you take the Euclidean norm, but you multiply by 2 over 1 plus r squared, r being the distance of the base of the vector to the origin. So the claim is that if you calculate the length of a vector in R2 using this formula instead of the usual Euclidean one, you will end up with precisely the length of the corresponding curve on the sphere. And that is what we wanted. Just to convince you that this is true, I want to go back to that example where this radial curve in R2 parameterized half of the circle on the sphere. So the length of that half circle on the sphere is pi, because you have 2 pi for the whole circle. It has radius 1. Half of it is pi. So if I compute the length of this planar curve with my new formula, I must get pi. So let's double check. So you have 0 to infinity of derivative, which is always 1, 0, with this new norm G. But remember, this G takes into account how far you are from the origin. So 1, 0 at time t0, that means you are t distant away from the origin. So 2 over 1 plus t squared, Euclidean norm of that. But this is always equal to 1, so it goes away. Now I happen to know the antiderivative of 1 over 1 plus t squared. That becomes arctan. Arctan of infinity is pi over 2. Arctan of 0 is 0. You end up with pi. And that confirms, at least it tells us that we haven't computed some nonsense formula. The reason why this is true requires, of course, some more advanced knowledge of Riemannian metrics. In the language of Riemannian metric, one would say I just pulled back the metric of the sphere onto the plane using this isomorphism psi between them. So all of this I did is compactified into that one sentence, pullback of the Riemannian metric. But I love this exercise because number one, it's hands-on, and number two, even if you are not that advanced in your knowledge of Riemannian metric, you actually can take it as a beginning step. A Riemannian metric here, G is a Riemannian metric. Let's see what it did. At every point of my space, there is a tangent to my space, which is a copy of Rn, n being the dimension of the manifold. So here we're talking about R2. The tangent space of R2 at a point is a copy of R2 attached to that point. And a Riemannian metric tells you how you dot product two vectors from that tangent space. So if you move to a different tangent space, you no longer identify. So this is unique about R2, that you know that this V here can be transported parallel to this V here. So you should imagine that this is not the case on a general manifold. So this V here has nothing to do with that V. And but a Riemannian metric tells you how you can multiply, that means dot product, any two vectors which belong to the same tangent space. And in our example, we just computed how we do it. And the dot product and the norms varied from one point to another. That means from one tangent space to another. But of course, you want also some compatibility, that these change smoothly. You don't have a completely different dot product on a tangent space that is nearby the other tangent space. And so, yeah, that can be regarded as your first step in understanding Riemannian metrics. So you can put it on a curved space. At every point there is a tangent space, a copy of R2, say if this is two-dimensional, and a Riemannian metric gives a recipe for how you dot product two things. And if you can dot product, you can talk about the norm by taking dot product with itself and then root. So I hope you enjoyed this exercise, and if you are advanced, on the other hand, you may want to compute the areas using this dot product. Can you compute areas in R2 using this metric and confirm that it exactly gives you the area of the corresponding part or domain on the sphere? Thanks for your attention today, and I will answer any questions you put in the comments, and see you soon.